The radio frequency alphabet sign language system by Geoff Logue is an unprecedented invention designed to combine radio frequency transmission, keyboard communication, and sign language recognition into a unified, efficient, and secure communication framework. This system leverages the principles of electromagnetism, AI-driven gesture recognition, and advanced encryption to create a robust, multifunctional communication method capable of serving a wide array of applications, including military, emergency response, and accessibility enhancement. Fundamental design principles. Radio frequency mapping. Each letter of the alphabet, from A to Z, is assigned a unique radio frequency within a predefined and isolated spectrum band. This approach minimizes interference and optimizes signal clarity. Frequencies are allocated based on the following factors. Bandwidth management. The system operates in an isolated segment of the RF spectrum, such as UHF or VHF bands, to prevent collisions with commercial or public frequencies. Sequential allocation. Frequencies are assigned sequentially or in a pattern optimized for signal processing. For example, A equals 88.1 MHz, B equals 88.2 MHz, C equals 88.3 MHz, and so on until Z equals 91.0 MHz. Frequency modulation. Each key press or gesture transmits a modulated signal, like FM or AM, for precise frequency differentiation. Redundancy frequencies. Backup frequencies are assigned to ensure seamless communication in the event of interference. Keyboard integration. The system includes a programmable keyboard where each key, from A to Z, is hardwired or software configured to emit its associated radio frequency. Additional keys handle numerical inputs, special characters, and control commands, such as encryption toggle or signal mode switch. Multifunctional outputs. When a key is pressed, the system simultaneously emits the corresponding radio frequency, displays the character on a digital interface, and optionally encodes the transmission for secure communication. Sign language interface. A critical component of the system is its gesture recognition module for sign language input. Hardware includes cameras or LiDAR sensors that detect hand movements and shapes, and wearable devices like motion-sensing gloves enhance accuracy in low-light or high-noise environments. Software comprises AI models pre-trained on sign language datasets that recognize gestures corresponding to letters, numbers, and symbols. Advanced pattern recognition algorithms map gestures to their radio frequency equivalents. The software also allows for customization to support regional variations in sign language, such as ASL, BSL, and LSQ. Communication modes. Typed mode. Users type directly on the keyboard, and each keystroke emits its corresponding radio frequency. This mode is ideal for rapid, high-accuracy message transmission in noisy or low-visibility environments. Gesture mode. Users perform hand gestures corresponding to letters or phrases. A gesture is captured, interpreted, and transmitted as a radio frequency signal. For example, the gesture for A triggers a signal at 88.1 MHz, which is broadcast to receivers. Hybrid mode combines typed and gestural inputs for maximum flexibility. For example, a user types a message but supplements it with gestures for emphasis or redundancy. Transmission and reception. Signal encoding. To enhance security, all transmissions can be encrypted before being broadcast. Encryption options include AES 256 or RSA algorithms, which ensure that only authorized receivers can decode the signal. Dynamic frequency hopping, rapid switching between frequencies to avoid detection or jamming. Time-based one-time pads, or OTPs, add an extra layer of security by using time-synchronized keys. Reception receivers equipped with frequency demodulation technology decode the transmitted signals into readable text or audible speech. Advanced receivers also support real-time error correction for signal disruptions and multi-channel support to receive simultaneous transmissions from multiple users. Let's dive into the technological components that make this system so advanced. First up, the hardware. The keyboard is designed to be durable and ergonomic, perfect for use in extreme environments like military operations or emergency zones. It features an integrated RF transmitter with an adjustable range, ensuring reliable communication. Next, we have the gesture recognition system. This includes high-speed cameras equipped with wide-angle lenses and motion-sensing gloves that come with gyroscopes and accelerometers. These tools work together to accurately capture and interpret gestures. There's also a portable receiver. These can be wearable devices or handheld units, specifically tuned to decode the RF spectrum used by the system. Now, moving on to the software. The AI-powered gesture recognition is truly impressive. Neural networks, trained on thousands of sign language gestures, provide fast and accurate interpretation. Plus, adaptive learning algorithms personalize the system to the user's unique signing style. For signal processing, the system uses advanced algorithms to minimize noise and enhance clarity. It also employs real-time frequency hopping to ensure secure and uninterrupted communication. And there you have it, the technological components that power this incredible system. Applications, military operations, enables silent, secure communication in combat scenarios, integrates seamlessly with existing communication networks for redundancy, provides an alternative to traditional verbal or text-based systems, accessibility, empowers individuals with hearing or speech impairments to communicate effectively in radio-based systems, bridges the gap between sign language users and non-signing counterparts, emergency response, facilitates communication in disaster zones where verbal communication may be impossible, enhances coordination among diverse teams with varying communication abilities, covert and tactical missions, combines the silent nature of sign language with encrypted radio transmissions for maximum discretion. Challenges and solutions. Frequency interference. Challenge overlap with existing radio communications. Solution. Allocate dedicated frequency bands and use dynamic frequency hopping. Complexity. Challenge training users in both sign language and system operation. Solution. Provide intuitive user interfaces and modular training programs. Cost. Challenge. High initial cost of hardware and development. Solution. Focus on scalability and modular designs to reduce production costs. Future enhancements. Quantum communication. Integration of quantum encryption to make the system virtually unhackable. AI-driven adaptation. Continuous improvement of gesture recognition through user feedback. Wearable tech. Miniaturization of components for seamless integration into wearable devices, such as smart glasses or wristbands. Global standardization. Development of universal standards for frequency allocation, encryption, and gesture recognition. Extreme potential. The radio frequency alphabet sign language system represents a leap forward in human communication technology. By seamlessly integrating RF transmission, typing, and gestural inputs, it addresses challenges of accessibility, security, and adaptability. With proper implementation and refinement, it could revolutionize communication across military, civilian, and commercial domains, making it one of the most versatile systems of its kind.